All right, so here is your key to your classroom test for 112 to 114. So number 1 says, let G be a function that is a transformation of the function f such that G is equal to this right here. We're going to describe the transformations of f that result in the function G. So we're going to write them down from left to right. Looks like I only have 2. So that first one is going to be a vertical dilation. Dilation by 3. Remember, that is a vertical stretch, but College Board likes the term dilation. And then that 2 there is going to be a horizontal translation of 2, because we would be going to the right 2, so of a positive 2. All right, let K be a function, so such that it's a transformation, so of H, so we have this here. We're going to describe the transformations. Looks like I have 2 here as well. So that 4 is inside there with the X, so that is a horizontal dilation by 1/4 because X is a liar, and that 1 is on the outside, so that is a vertical translation. Ooh, can't spell. Translation of -1, meaning I'm going down 1. Okay. Let R be a function. Okay, so we're still just describing transformations here. So I have 1, 2, 3 here. Now this x over 2, I could rewrite this as R of x equals 5 times p of 1/2 x plus 3. So I don't make anything up as I'm doing my transformations. So first I have that 5, that is a vertical dilation. By 5. Then that 1/2 is going to be a horizontal dilation by 2, because x is a liar, and that 3 is a vertical translation of 3. All right. Then we have this one here. Looks like I have 3. I have a reflection, a dilation, and another reflection. So that first negative is going to be a reflection across the x-axis. That 2 is going to be a vertical dilation of, or by 2, because y does not lie. And then that second negative is going to be a reflection across the y-axis. Okay. All right. Then we have the table below gives values for function f at selected values of x. Use the table to answer 5 and 6. All right, so A is g of 3. So g of 3 is going to be equal to, here's my g function, f of 3 times 3 plus 2, excuse me. Oh, I'm writing entirely too big. Let me redo that. So g of 3 is equal to f of 3 times 3 plus 2. So So 3 times 3 is 9, so it's really f of 9 plus 2. F of 9 is negative 6, so I get negative 6 plus 2 gives me a negative 4. All right, then g of negative 1, give me g of negative 1 is going to be equal to f of 3 times a negative 1 plus 2. So you're literally just substituting it in here. We don't worry about who's a liar and what. It all takes care of itself. So this becomes f of negative 3 plus 2. F of negative 3 is a negative 1 plus 2 is 1. All right, so then here is h of x. So h of 3 is going to be equal to negative 2 times f of 3 plus 3. That gives me negative 2 times f of 6. F of 6 is 5. So this becomes negative 2 times 5, which is negative 10. Then h of 0 be equal to negative 2 times f of 0 plus 3. That's really just negative 2 times f of 3. F of 3 is negative 2, so it's negative 2 times negative 2, which is a positive 4. All right, flip it over. Now, I know this spacing is weird, and I probably should have put some lines here, but this question does not go with this graph, and here's how I know for sure. This talks about function k is constructed by applying 3 transformations to the graph of h in this order. A horizontal dilation, blah, 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 talks about k of x, h of x. Nowhere in number 7 does it refer to f of x, and this very clearly shows a graph of f. So be very careful on those things. Make sure you're using the correct things when you're doing this. So let me go back and actually do number 7 now. Function k is constructed, all right, so k of x is equal to, it says a horizontal dilation by a factor of 1/2. So x is a liar, that's a horizontal dilation, so this is going to be h of 2 times x. A vertical dilation by a factor of 3, so that gets multiplied on the outside, and a vertical translation by a negative 5. And it's asking you for the values of A, B, and C. Here's where you have to be very careful on these. They didn't have like a plus or minus in here, but make sure that you are, looking at this and able to take out A, B, and C like it's asking you to. So here A is 3, B is 2, and C is negative 5. Okay. Now we get to look at the graph. Graph goes with number 8. So the graph of y equals f of x, there's the graph of f, consisting of 3 line segments, is shown for this. Sketch a graph of g on the same axis above, where we have this right here. Okay, so what's going to help you the most here is let's talk about what's happening here. We have a horizontal translation of negative 1, because we're going to the left, and a vertical translation of negative 2. Okay, so then we look at what affects x and what affects y, right? So I have this point xy, it's going to be mapped to, so my horizontal translation, this is an x, this is a y, right? So that means I end up with x minus 1 and y minus 2. Right? And then you can make a little t-chart. I would suggest maybe doing this. Yes, you can also just count on the graph. It kind of depends on how the question's being asked. So I'm going to just do all of this because you might need one part, better than more so than the other, depending on how the question's actually asked. But this is x and f of x, okay? We're going to pick off key points here. So at this point here, that's -4, -3. -4, -3. Then I've got this point here. That's -1, 1. I've got this point, which is 2, -1. I've got this point, which is 4, 3. Okay. Then I'm going to do x and g of x. Okay. So remember, this basically represents f of x, and this represents g of x. Okay. So for each one of these, I'm going to take the x for all the x values. I'm going to subtract 1. So this is -5, -2, 1, and 3. And for all the y values, I'm going to subtract 2. So that's -5, -1, -3, and 1. And then that gives me my new points to plot here. Go to -5, -5, -2, -1, 1, -3, and 3, 1. So then when I connect the dots, then it should look the same size and shape because I didn't have any dilations there. And there you go. All right, let's look at number 9. What do I have here? So graph of f of x again. 3 line segments. Sketch a graph of h on the same axis above. Here's h. So here I have a vertical dilation by 2, and I have a reflection across the y-axis. Okay, so I have my xy, to figure out what that's going to map to. All right, so this affects y. This, even though I'm reflecting across the y-axis, that's because I'm changing the sign on x. So this is going to be -x and then 2y. So again, to kind of be safe, it's good to write stuff down. I'm going to have my x and f of x, and then we will have x and h of x. Oh, goodness gracious. X and h of x. So I'm going to pick off my key points here. Got one at -3, 3. One at -1, 3. One here at 1, -2. And one here at 4, 1. All right, so then these are my xy, this is my f of x, right? This is my h of x. So basically every x value from f, we just change the sign, so this becomes 3, 1, -1, -4. And then all the y values get doubled, so this is 6, 6, -4, and 2. Then I plot those points. Go to 3, 6, 1, 6, -1, -4, and -4, 2. Then I can connect the dots. And this is a different size and a little bit of a different shape because it got stretched and obviously it got reflected. And you could do a much better job with your straight edge if you needed to. Your ID makes a great straight edge when you're doing those. Okie dokie, we got one more of these. All right, so I have, write out my transformations here. I'm going to reflect across the x-axis. Then I have a vertical dilation by 2. I have a horizontal translation of -3 because I'm going to the left, and I have a vertical translation of 1 because I'm going up. All right, so my xy, which is f, is going to map to some ordered pair, which will be k. So when I'm reflecting across the x-axis, I'm changing the sign on y. Vertical dilation, that's y. Horizontal translation, that's x. Vertical translation, that's y. So the only thing happening to x, vertical translation of -3, so it's x minus 3. Remember, when it comes out of here, x isn't lying anymore. It only lies in function notation. Then I've got 3 things that are going on with y. I've got to reflect it, so that's a negative, vertical dilation of 2, and I have to add 1 to it. Right. So I'm going to do my x and f of x. I'm going to do my x and my k of x. All right, so pick off these key points. Oh, I guess those are the same as the other ones, but -3, 3, -1, 3, 1, -2, and 4, 1. So for my x values, I'm subtracting 3 from each one of them, so that's -6, -4, -2, and 1. For my y values, I'm multiplying by a -2 and adding 1, so this would be -6, which makes it -5, and that's -5. Multiply by a -2, get a +4 plus 1 is 5. -2 plus 1 will be -1. Okay, then I can plot those points. -6, -5, -4, -5, -2, 5, and 1, -1. Okay, so then I'm going to connect the dots. Oof, pretend like that's straight. It's hard to do on this board. And it looks something like that. Alrighty. Number 11. So domain of the function, the range. So I'm going to rewrite these in the -5 to 10. Oh my goodness. This is x, so that's my domain. And then -4 to 2. And this is y, so that's my range. Got 2 things going on here. So you can write out your transformations like we did up there, but you don't necessarily have to. I didn't necessarily have to on that either. If I look at everything that's happening to x, the only thing that's happening to x is this right here. We're moving to the right 5, so this is x plus 5. And then this is the only thing happening to y, so that's y plus 7. I'm telling you, you want to write that out, or some of you are just going to do what this says and subtract 5, and that is not what is happening. So then for the domain, because this is my domain, this is my range, my new domain, I just take these 2 and add 5 to both. So -5 plus 5 is 0, and 10 plus 5 is 15. Just moved it over to the right 5. My range, I'm just going to add 7 to both of these. This is going to give me 3 and 9. Just moved it up. Okay, so I'm going to rewrite these as well. -4 to 8. Oh, why do I keep doing that? This is x, so this is my domain. And then -7 to 3. This is y, so this is my range. And if you want to rewrite this, I mean, you can. Just make sure because you need to understand what's happening here. R of x is equal to 2 times k of, that is 1/3 times x plus 1. So my xy is going to map to, and the only thing happening to x right here is this horizontal dilation. X is a liar. When we take it out of function notation, all the lies are revealed. We're really multiplying 3 times x. And then these 2 are what are happening to y. And so that is going to be 2 times y. plus 1. Now, again, if you can go straight from here to here, that's great. If you're afraid you're going to mess it up, then maybe you want to actually write out these words like we did up here. I mean, that's up to you, but just make sure you can get the right answers out of this. So for my domain, I'm going to just multiply each x value by 3. So this is negative 12 and 24. And then for my range, I need to multiply each number by 2 and add 1. So that would be negative 14, which is negative 13. And then 6 plus 1 is 7. And what I failed to say is for all of these, you need to make sure after you write them that they make sense, that they are going from least to greatest. If not, all you have to do is flip them around. That's it. Okay. All right. Let's look at 13 here. I'm going to rewrite this. Negative 10 to 0. That's my domain. Negative 8 to 6. That's my range. Okay, and then my xy is going to map to... All right, so this is the only thing that is happening to x. That is a horizontal dilation of 1/2 because x is a liar, so all the lies are revealed when we take it out. And then this is affecting y, so this is negative 3y. Okay. So my domain then, what I am doing is multiplying both of those by 1/2, so that becomes negative 5, 0. My range, I am multiplying by a negative 3, so this would be a positive 24, and a negative 18. Okay, then I check. Least to greatest, good. This is not least to greatest. That's because we had a reflection, so all I have to do is flip that around. Just write it correctly, least to greatest, and then you're good. Otherwise, your interval doesn't make any sense. All right, so now onto the calculator part. Okay, so it says the table above provides data for 7 ordered pairs. Which function type best models the data in the table, linear, quadratic, or cubic? Explain your reasoning. Explain your reasoning, or explain your answer using characteristics from the data in the table. Even though this is on the calculator part, this particular kind of question would most likely be on the non-calculator because we're not trying to just type in stuff and then look at it and see what we think. Because if you do that and you type it in, you can say, oh, because that's what fit the best and does most. Like, that's not what they're asking. It says characteristics from the data in the table. We do not need a calculator for this. You should be able to answer this question without one. So we look at our x values. Our x values are clearly increasing the whole time, which is what we expect. My y values, we start off at 40. We decrease to like about 2.1, and then they start to increase again. So if my y values are decreasing and then increasing, that screams quadratic, right? But we have to make sure we use our words appropriately and understand how to explain this. So we can say it is quadratic, or we think it is quadratic. All right, because our y values decrease to a minimum. I always make that look like it's one word. To a minimum. Because one of the stipulations to be a quadratic is that it decreases to a single minimum or increases to a single maximum. And that's all we see in our data. So according to the data we have, this is what we think is the best. So our y values decrease to, and then at 2.1 they start to increase again. That does not necessarily mean that this is my minimum. It should be close to that, but we're not guaranteed that. There's nothing in here that says that for sure. So we would say to a minimum at about, because it should be close, x equals 5. Okay, so our y values decrease to a minimum at about x equals 5, then increase, and that is not the only stipulation. We also have to say and are roughly symmetric. Okay. and are roughly symmetric. Because I start here at 40, y value of 40, I decrease to something close to 2.1-ish for my y value, and then I increase again to about 39.5, and this is like at 40. So if you look at these, I mean, they are roughly symmetric. And we say roughly because if it's real data, it's not most likely not going to be exact. Whereas if we just had a function and we knew exactly what the function was, then it would be. But those are the words that you need. Okay, so now it says, write an equation for the regression model for the data in the table. So this is where we go to Desmos, and we are going to add a table, and we're going to add our x values, 0, 2.5, 4.1, 5, 6.1, 7.5, and 10. Okay, so I'm going to double check my x values before I do my y values. I think that looks good. It's so easy, especially on the little thing I'm using to punch in something wrong. All right, so then we have 40, 11.5, 3.4, 2.1, 3.7, 11.25, and, oh, see, I wasn't looking up here. Okay, let me go back to here. And okay, at 4.1, what was I supposed to be? 3.4. And then that is supposed to be 2.1. That should be 3.7, 11.25, and 39.5. Okay, let me triple check these. Goodness. Okay. So then the next thing I want to do, I'm going to hit my little magnifying glass there. Now I've already decided that I think quadratic looks good, so that's what we're going to be using. Linear is your default, but I want a quadratic regression. And then I'm supposed to write it correct to 3 decimal places, and so this is what we have here. I'm just double checking one. But remember, if you only had like 2 decimal places, you want to use a little 3 decimal place, or the 3 dots right there. Export is custom regression. And then we have this right here. Okay. And I just realized that I have something written wrong. Okay. So sorry, I was just fixing my notes before I had to click back over to the other page. Since we saw 3 decimal places right here, I didn't have to put this part in, but what I want you to see before we do that is that this says 1.509. If I truncated here, this would be 1.508 or 5085, and whether you put 1.509 or 1.508, it would be okay. I highly, highly, highly encourage you not to round ever, so you don't do something ridiculous. Just truncate and move on. But this was rounded for you, and that's okay. As long as you can see 3, you're good with whatever, because they would take your answer either way. So if we just wrote down what we saw from that Desmos gave us, since it was 3 decimal places, we would have y equals 1.509 x squared minus 15.138 x plus 39.997. And if you put down 4 decimal places because you saw more of them, that is absolutely fine. But again, as long as Desmos gives you 3, you can use 3 and use whatever they have, and that's fine too. Okay, so then we're asked for the residual. Okay, so residual, remember, you were in an AP class. It is the actual minus the predicted value. Okay, so the actual value comes from the table, and it says x coordinate is 6.1. So if my x coordinate is 6.1, then 3.7 is the actual data that we have. So we're going to have 3.7 minus, and then we're going to look over here. All right, so I need the actual, or what my function says is happening at 6.1. So I can type in x equals 6.1, okay? And then I have this line in here that it gives me. And when I click on this, look what I get. I get 3.7 because it doesn't know if I'm asking for the graph or if I'm asking for the actual point. So the chances of them being the same, I mean, it's possible, but it's highly unlikely. And what I want is I want the function to tell me that the red curve that I see, not the green dots that I typed in. So here's the thing, okay? And this is one thing that actually makes the calculators a little bit better than this, because I can go back up here and I can ask this to export my equation right here, and I can change that to f of x, and then I can evaluate it at that point. The problem is that Desmos is using these this rounded value and these. So I'm going to show you what happens, but this is not what I would actually want you to do. So let me just show you what I'm talking about here. So if I back that out and I call this f of x, okay? Then in my next little thing here, I can do f of 6.1. And you see how it gives me that 3.80 number right there? That is way off from what I should be getting. And I know that because I know what the answer is when we actually do it on the calculator. Okay, this is why rounding in the middle of things is bad, real bad. Okay, so I'm showing you that to show, so we can get that number, jot that number down somewhere because it's not right, but write it down. Okay, and we're going to come back to that. So I'm going to X this out. What I want to do instead is this. Even though here it's only showing me like 4 or 5 decimal places, it's actually storing the rest of them, just like things get stored in the calculator. And so I have what this regression is. I'm going to build my own. So I'm going to do f of x equals, okay, and I'm basically going to type this in. Instead of putting this number, I'm going to put a because it's going to be whatever that is. So ax squared, and I'm not putting the little subscripts and stuff because I'm not asking it to find the regression. It already did. I'm just telling it to give it to me with the exact values. So then bx and then plus c. So basically it showed me what this looks like right here, but with truncated and rounded values, but we cannot use those or we are way, way wrong. And so now that I have this, notice I got rid of the other f of x. Now I can do f of 6.1. And notice that my other number was 3.80509. This is 3.7855. That's way different, okay? And even when I go to actually put my answer, now I'm going to write down that I'm going to subtract 3.7855. And if I subtracted this, it's going to come out just fine for what I need. But if I wasn't sure, then I can do this. What I want, that is that 3.78 number. I really wanted 3.7 minus that, right? I can do that right here. 3.7 minus that right there. There's my residual. My actual minus my predicted. Okay, and it just did it for me. Now I should write down like basically what I'm doing here, but remember, just because you write down a rounded number, just like we did here, doesn't mean we're going to use those. It's just telling us what is kind of happening there. And so then this is negative 0.0855 or 0.085, and that is my residual. Now let's revisit the x equals 6.1 thing that we did, okay? So if I have x equals 6.1. Okay, and I'm going to change that from red so I don't get confused about what I'm looking at. Let's make that purple, blue, whatever it is. Okay, so remember the problem was if I do this, I just get 3.7. But there's another option. You can zoom in, and if you zoom in and then you touch that, you see that 3.8755 number right there. And if all you're doing is subtracting, if you use 5 decimal places, you will be correct to 3 in the end, regardless of what else is happening. So I could use that number there. I mean, that's, like I said, that's another option here. I hesitate for you ever to use a rounded or truncated number because I don't know that y'all always understand when you can and when you can't. But if you have enough decimal places, you are usually going to be correct to 3. So I could write down all 5 of those and then do my subtraction, which, as you can see here, even just using 4, I'd be correct. Or even just using 3, I'd be correct, just by the nature of the numbers, as long as there's no rounding and nothing else weird happening. But again, I don't know that we all have enough experience to really know when that's allowed and when it's not. So we need other options here. And we will play with that more, and we will do more with that. I would have done more when I actually taught it, except I didn't realize that Desmos was using rounded stuff, because that's really bad and a little scary. Okay, there you go.